Hi, I'm Fishing Ball and welcome to part 1 of lesson 4 of my tutorial series on QMD. Over this entire lesson, we'll see how to make even more formal ores via the mass spectrometer, collide particles with the collision chamber, decelerate particles to suitable energy with the decelerator, produce antimatter with the exotic containment, and finally, perform fusion with the nucleosynthesis chamber. In this part, we will talk about the spectrometer and then make a multi-block setup of suitable beams for the next part, where we'll synthesize antimatter and perform fusion. The mass spectrometer is an auxiliary accelerator type multiblock that can quadruple ores, extract more byproducts, and split various items and fluids into their constituent elements. By default, it processes one item every 25 seconds, but depending on its size, it can process faster. The principle of the spectrometer is to take in items or fluids, split them into ions using biscomagnet rings, and then recollect the ions via beam blocks. On the inside of the mass spectrometer, we place alternating layers of bisco rings and beam block squares, and for every sandwich of bisco ring beam blocks bisco ring, the process speed increases by a multiplier of 1. To build an MS, we need to make a frame that is 7 blocks tall, 7 blocks wide, and 5 blocks long, plus 2 blocks for every process speed multiplier above 1. For example, if you want an MS with a process speed of times 4, we need a frame that is 7 blocks tall, 7 blocks wide, and 11 blocks long. Let's build a 7x7x7 MS, which will have a process speed of times 2, or 1 item every 12.5 seconds. Here's the frame. It's missing the front face, so I can place all of the magnets and stuff on the inside. And now, let's bring up, as you can see, we have a magnet layer, then a beam layer, then a magnet layer again. So, a beam layer is simply a 5x5 square of beam blocks, and a bisco layer is made out of a 3x3 square of yoke blocks. And then we surround that with bisco magnets. Then we just place a square of beam blocks. And we just repeat this pattern until we reach the end of the multiblock. We always start with a bisco layer, and we will always end again with a bisco layer. Let's make sure the entire multiblock is full, and then we go to the next step. Now that we filled the inside, we will build the outside. So, we need, of course, a controller, we need a energy port, and we need 2 coulomb vents, because it's an accelerator type multiblock, so we need all of these as per usual. Now, for every single beam layer, you will need to do the following. You will need to first place on the bottommost block a laser ion source. This thing right here. And then above it, you will need to place 4 ion collectors. You will need to do this exact setup for every single beam layer that you have. So in our case, we have 2 beam layers, we have two of those. So I'll just print everything really quickly and also place coulomb vent here, and the MS has formed. As you can see, speed multiplier times 2. Now, since the MS is an accelerator type multiblock, it requires a redstone signal to turn on. And since it has bisco magnets, we can use liquid nitrogen to cool to anode helium or neon. All you need to do to start operating, you need to input the items or fluids in the laser ion sources, and with the ion collectors we can collect items and fluids that are output. We did this little detour of showing this mass spectrometer because we're about to ramp up the resource cost for our setups by a lot. So we need all the ore multiplication and all the byproducts we can get. And now let's move on to the collision chamber. So for the next lesson, we need to produce a muon beam, which will be used to perform fusion in the nucleosynthesis chamber multiblock. And we need to make an electron beam and a positron beam, which will then recombine to get positronium, and we'll then store that in the exotic containment chamber. To get all of these particles, there is a variety of ways we can do this. But a simple way, although it doesn't produce a lot of positronium and doesn't give us a lot of muons for fusion, is a proton-proton collision. The proton-proton collision recipe is the bottom recipe here. It happens at relatively low energies, only about half a gigaelectron volt, so that should be pretty easy to design for. And it produces the two protons, a pion plus, a pion minus, and a pion naught. The pion naught can be decayed twice to get electrons and positrons, whereas the pion minus can be decayed once to get muons. It's a pretty simple recipe. So the plan is the following. We're going to start with a LINAC to get protons up to speed. Then we're going to put them in a synchrotron to speed them up and get them to collision energy. And then we're going to use a splitter. This means that we will have the same beam split into halves, and we will not need a second LINAC and synchrotron setup. But of course this means we will need a few extra diverters to get the two halves back together. And then using extra diverters and decay chambers, we will then produce the required particles. I will not talk in this video about how I designed everything, but feel free to ask if you want. So here's the setup so far. This is LNAC, then we've got the synchrotron. The synchrotron speeds up particles, gets them into the splitter then sends particles in that direction and in that direction. And here in the middle we have a suspiciously collision chamber sized hole. The collision chamber is a particle chamber type multiblock where particles can collide, often violently, with other particles to create new exciting states of matter. Collision chambers have a collision energy stat. This is the energy in which the collision takes place, and it is this energy that must be between the energy range of the recipe as seen in J. The collision energy is calculated as 2 times the square root of the product of the input beam's energies, or in short, 2 times the geometric mean. And now let's see what happens with the stats of the output beams. In every collision recipe, you can expect to get between 1 to 4 different beams. The amount of the output beams is equal to the minimum of the input beams PU per tick times the amount written on the recipe times the overall output efficiency. The output efficiency is equal to the minimum between 1 and the product of the cross-section times the chamber efficiency times 1 minus the absolute difference of the input beam's energies divided by their sum. This means that to get the maximum PU per tick on the output, we need to have input beams with the same PU per tick and the same energy. The energy is calculated in the same way as target chambers, where input energy is the collision energy, the energy released is the same, and of course we divide this sum by the total PU released. For focus, the beam length is considered as the chamber's internal length, so it's 15 blocks, plus the chamber's diameter minus 1, and that's divided by 2. For example, a chamber with dimensions of 7 by 7 diameter and 17 blocks long has a beam length of 15 plus 7 minus 1 divided by 2, 18 blocks. Then the focus is simply the minimum of the input beam's foci minus the focus loss per block of the output beam times the beam's length. And now we're ready to see how do we build the collision chamber. The collision chamber is a cuboid multiblock which has a diameter of 5 by 5 to 13 by 13 blocks. It has to be odd numbers only, and you can go bigger than 13 by 13, but there's no point because you cannot place any detectors beyond that point. And it's also 17 blocks long. We're going to make a 5 by 5 by 17 collision chamber. The frame is right in front of me. Let's print it. And then let's place the ports. We need 6 ports. We need 2 input ports on the center of the faces of the short faces. And then we need to count 2 blocks on the long faces from either end, so 1, 2, and then we need to place an output port. Then we need to place a line of particle chambers connecting the two input ports, which of course happens to go through the middle of the multiblock, just like we've done with beam blocks lines in the synchrotron and the LINAC. Then we need to connect this particle chamber line to the output ports using beam blocks. There we go. And now we can place detectors, we can place the controller and an energy port. Of course, we'll place detectors here because the cross-section is only 10%. And we're good to go. Give it some power. And we have collision happening. Now, where does each particle in this recipe exit? Let's first name the particles. The proton is particle 1, the pion is particle 2, the pion minus is particle 3, and the pion naught is particle 4. Let's go up from the target chamber, and then let's see with F3 which direction is our target chamber in. As you can see, it is a north-south collision chamber, and the positive direction is towards south. This is important because I'm going to now put a chart on screen. We can see the number each port corresponds to and the positive direction which is used to number each port. As you can see, the ports don't quite correspond with the particles as we named them. So over here we get particle 1, over here we get particle 2, over here we get particle 3, not particle 4 as you might have expected. And similarly here we get particle 4 instead of particle 3. And here's a proof. Pion 0 comes out of this port, which we named particle 4. And here you get pion minus, which is particle 3. An important utility of collision chambers is the ability to switch ports. Since recipes can output several particles, but you need those particles to output from specific ports due to how you've built the overall setup, it can be useful to know how can we change where each particle is output. Let's go back to the collision chamber chart. The physical outputs are labeled A to D, and the particles are labeled 1 to 4. Each port is connected to the one next to it clockwise as indicated by the curved arrows. Shift right-clicking a physical port with the multitool makes it switch the output with the next clockwise physical port. So, for example, if we were to right-click port A, it would switch places with port B, and so protons would output out of port B, and pion plus would output out of port A. Let's see this in action. Let's try to bring pion plus outputting from port B to output in port D. First, we need to switch port B with port C to bring the particles into port C, and then we switch port C and port D. And so, right-clicking with the beam meter on port D, we get pion plus. Of course, we can just do the reverse steps to bring everything back to normal. And as you can see, pion plus is back in its original spot. And that's how you can change where each beam is output. Collision chamber recipes tend to output their particle beams with very high energies, but the multiblocks that we'll talk about in the next video require particles to have very low energies, ideally 0. So we need some multiblock that is able to reduce the energy of particles. Enter the Decelerator, an accelerator type multiblock that can reduce the energy of input beams. It is designed and constructed very similarly to a synchrotron. To design a decelerator, we need to use the dipole field strength equation from synchrotrons. This equation tells us the maximum particle energy the decelerator can handle, and of course, the particles must have a charge in order to be decelerated. Decelerators slow down particles to an energy described by the following equation. 1 minus redstone signal strength to the controller divided by 15 times the maximum energy. This means that a full strength signal decelerates particles down to zero energy. A partial strength redstone signal will decelerate particles down to an energy that is a fraction of the maximum level. Now, if a particle happens to have a lower energy than this intermediate level, then nothing will happen. The particle will not get accelerated to the higher level and will stay at its original energy level. In terms of construction, the decelerator is very similar to a synchrotron, but it has the following changes. First of all, you need the decelerator controller. That goes without saying. Second, you cannot use synchrotron ports. These are synchrotron exclusive. Finally, you must place at least one RF cavity whose strength does not matter. You can use aluminum, you can use copper cavities, just use the cheapest possible. Of course, you only need one. You can use extra if you want to achieve better cooling, but they just waste power and produce extra heat. So here is an example decelerator. You can clearly see that it's pretty much a synchrotron in all but name. The 4 current dipoles, the ring going through the middle, the square donut formation, 2 coolant vents, power port, a decelerator controller, and that's pretty much it for the decelerator. We saw how it works, we saw how it is constructed, and now we're going to move on to the outro. Okay, so let's explain what we did since the last cut. We've got the P 0 particles coming through here, decaying twice, going into the decelerator, and then exiting from here, and here's going to place our antimatter chamber. Whereas the muons, they come from here, they go up and into the decelerator, and then the fusion will occur in this multiblock that will be placed over here. And so as you can see, we're starting to truly capture the essence of QMD, making large, complicated setups consisting of many multiblocks and crazy resource costs, simply to make antimatter and also to make fusion. So what did we see in this lesson? We saw how the mass spectrometer works, we saw the decelerator, and we saw the collision chamber. In the next lesson, we'll see how the nucleosynthesis chamber works and how the antimatter containment works. Until then, I will see you in the next video. Goodbye.